All right, let's dive into one of the most fundamental ideas in all of chemistry. We're going to see that chemical reactions aren't just things bumping into each other randomly. No, it's more like a carefully choreographed dance between two very specific partners. So, what actually sets the stage for this chemical dance to even begin?
It's a huge question, isn't it? But, at its very core, it's all about a simple exchange, a push and a pull of electrons. And to really get that, we need to meet the dancers themselves.
So, I want you to think of a chemical reaction like a stage play. Before the main event happens, everyone needs to know their part, right? Well, in chemistry, it's exactly the same.
We basically have two main roles. There's the substrate, that's the molecule we're really focused on, the one we want to change. And then there's the reagent, and that's the one that causes the change. And these reagents, well, they can be split into two very distinct categories, and they are the absolute stars of our show today.
Okay, first up, let's meet our first dance partner, the electrophile. The name itself gives you a massive clue. Electro for electron, and phile comes from a Greek word meaning loving. So this is our electron lover, or as I like to call it, the electron-seeker.
To put it simply, an electrophile is a molecule that just loves electrons. Its whole purpose in a reaction is to find a pair of electrons and accept them from another molecule. It's almost like it's searching for a partner to finally feel complete.
So what's its personality like? What makes an electrophile tick? Well, first, it's electron deficient. It just doesn't have a full set of electrons to feel stable. And because of that, it's always actively seeking electrons from anywhere it can get them. Which means, logically, it's going to attack other molecules right where they are most electron-rich. It goes where the electrons are. Simple as that.
So what do these things actually look like? Well, the most obvious ones are positively charged ions, like a bromonium ion. I mean, that positive charge is basically a giant neon sign flashing, "I need electrons." And this is where it gets really interesting. Electrophiles can also be totally neutral molecules.
Now check this out, because it shows how a neutral molecule like aluminum trichloride, AlCl3, can be an electrophile. See, the action is all happening right on that central aluminum atom. It only has 6 electrons in its outer shell, but it desperately wants a stable set of 8. So that spot, right on the aluminum, is what we call the electrophilic center. It's the exact point of attack for any incoming pair of electrons.
Of course, every seeker needs a provider. An electrophile can't dance alone. It needs a partner. And that partner is the nucleophile. If the electrophile is the electron seeker, then the nucleophile is the generous electron donor.
Let's look at the name again. Nucleo for nucleus, and phile for loving. This one is a nucleus lover. But why? Well, because a nucleus is positively charged, and the nucleophile has extra electrons it would love to share with that positive center. Its whole job is to donate its electrons to form a new bond.
And as you can probably guess, its characteristics are the total opposite of the electrophile. A nucleophile is electron-rich. It's got a surplus of electrons, either as a full negative charge or as what we call a lone pair. It's just eager to donate this electron pair, so it goes looking for and attacks electron-deficient centers, which, of course, are the exact spots it finds on electrophiles.
And again, we can see this in the examples. A hydroxide ion, OH-, is a classic nucleophile with that obvious negative charge. But just like with electrophiles, neutral molecules can totally play this role too. A simple water molecule, believe it or not, is a fantastic nucleophile.
So where's the magic happening in a water molecule? It's all on the oxygen atom. That oxygen has 2 lone pairs of electrons just sitting there, not doing anything in terms of bonding. This makes it an incredibly electron-rich, nucleophilic center, just ready and waiting to reach out and form a bond with an electrophile that comes along.
And this brings us to the whole point, right? This beautiful symmetry. Electrophiles are the electron-deficient seekers. Nucleophiles are the electron-rich donors. One accepts, the other gives. They are, quite literally, the perfect chemical match.
Okay, so we've met our dancers, we know their personalities. Now let's see what happens when the music actually starts. It's time to watch them finally meet on the chemical dance floor. This reaction is the perfect example. So on one side, we have ammonia, our nucleophile. It's got that lone pair of electrons sitting on its nitrogen atom. On the other side, we have boron trifluoride, our electrophile, with that super electron-deficient boron atom. The dance begins with the attack. The electron-rich nitrogen goes after the electron-deficient boron, and the result? Bam! A brand new bond is formed, creating a single, stable molecule. That's the whole dance, right there in one simple reaction. Okay, so why do we even bother with all of this? Why classify everything this way? Why is it so important to know who the electrophile is and who the nucleophile is? Because this is not just a naming exercise. This framework, this dance between the electron donor and the electron seeker, is the fundamental principle behind a massive number of chemical reactions, especially in organic chemistry. If you can identify the nucleophile and the electrophile, you can start to predict how molecules are going to interact and what they're going to make. It's almost like having a cheat sheet for chemistry.
So the next time you look at a chemical equation, don't just see a jumble of letters and numbers. Look for the dancers. Find the electron-rich nucleophile and the electron-seeking electrophile. Because once you understand the rules of the dance, you can start to predict the next move. What do you think you'll discover?